In Chapter 6, we will learn another important technique, vector quantization, VQ. VQ plays a very important role in speech signal processing. It is widely used in speech coding, speech recognition, and speech synthesis. Firstly, we should know the basic concept of quantization. Quantization is the procedure of constraining something from a continuous set of values, such as the real numbers, to a relative small discrete set, such as the integers. This is a function of analog to digital converters, which create a series of digital values to represent the original analog signal. The bit depth, number of bits available, determines the accuracy and quality of the quantized value. For example, digital signal processing involves taking an analog waveform, that is sound waves, and converting it to a series of individual samples, each of which has an amplitude value. The range of possible amplitude levels are defined by the bit depth. For example, 8-bit quantization equals 256 possible values. There are two kinds of quantization methods according to the quantified dimension. Scalar quantization is to quantize a single value or parameter. Vector quantization is to quantize a series of values or parameters. Why do we use vector quantization VQ method? In traditional signal coding with scalar quantization, the signal is first transformed into a sequence of parameters through a certain mapping of transformation, and then scalar quantization coding is performed one by one. In the coding with vector quantization, the input data is divided into several groups and quantized in groups. That is, these numbers in each group are regarded as a multidimensional vector, and then are quantized in units of vectors. The figure shows comparison of bit rates required by scalar and vector representations of reflection coefficients for 4 two-pole vocal tract frequency responses, H1 omega, H2 omega, H3 omega, and H4 omega. The 4 required reflection coefficients are highly correlated. The vocal tract is limited to only 4 configurations. Each configuration has 2 reflection coefficients. If we use scalar quantization, each reflection coefficient is quantized and coded with 2 bits. The total bits for all reflection coefficients will be 8 bits for all the 4 vocal tract frequency responses. If we use vector quantization, the 2 reflection coefficients in one group could be regarded as a vector, and the 4 vectors could be coded together with 2 bits. This is why VQ is suitable for lossy data compression. Scalar quantization is one-dimensional quantization. One amplitude corresponds to one quantization result. The quantizer is designed to divide the nominal amplitude into several intervals, which are called quantization levels. The sample values falling into the same level are classified into one category, and a quantified value named centroid is given. The quantization distortion D is the difference between the real value and the output centroid over the decision interval. The more quantization levels, the smaller the quantization error and the better the quality. Vector quantization is two-dimensional or even multi-dimensional quantization, and two or more amplitudes determine a quantization result. Taking the two-dimensional case as an example, the two amplitudes determine a point on the plane. This plane has been divided into n small regions in advance according to probability, and each region corresponds to an output result. The point determined by the input data falls within one decision region. The vector quantizer will output the centroid corresponding to that region. The quantization distortion D is calculated based on the input vector and the corresponding centroid over the decision region. The basic idea of VQ algorithm is to partition the whole feature space into a certain number of regions and use the center of a region to represent any vector falling into the region. The calculation will become looking up distance table if the table is pre-calculated before recognition. It will save some computing time. For doing that, it uses some clustering algorithm, like k-means algorithm, to iteratively get the clustering centers and the membership of vectors until convergence. The clustering centers will form the codebook. The membership of a vector will be a code label according to the minimal distance principle. Every vector inside the codebook will become a code word or code vector. There is an example of code word in two-dimensional space. Input vectors are marked with the symbol cross. Code words are marked with red spots, and the Voronoi region, encoding region, are separated with boundary lines. The space is separated into 13 regions. Any coordinate point xy, which stands for two-dimension vector, will fall into a specific area, that is Voronoi region, and then be approximated by red spots. The process of VQ is based on some kind of distortion measure, which matches the input vector with the code word in the codebook, and then uses the code word with the smallest distortion degree instead of the input vector. The code word with the smallest distortion will substitute the input vector. There are two questions: how to choose the proper distortion measure, how to design the codebook, and to generate the code words. Distortion measure is a measure of the error of distortion generated when the input vector xi is represented by the codebook restriction vector yi. It can describe the similarity between two or more model vectors. The input vector x can be represented with the code word zi, which is the centroid of the cell ci, if and only if the distortion measure between x and zi is minimal. This metric must be easy to calculate and analyze, and subjectively consistent, so that the difference represented by the distortion value can characterize the difference between the source signal and the transmitted signal. The most commonly used method is the Euclidean distortion measurement, which assumes that the contribution of the error generated by each parameter in the vector quantization to the whole distortion is equal. Generally speaking, unequal weights can also be introduced to the errors of different parameters to increase the influence of a certain component on the distortion. A common method in real applications is to use the inverse of the covariance matrix of Z for weighting. This distortion measure is called Mahalanobis distance, which is actually an exponential term in the Gaussian density function. Another method of weighting is to use perception-based distortion measure. This distortion measure uses the difference in perception of the human ear for two different signals, which of course is a subjective judgment. Perception-based distortion metrics have the following probabilities. Sound signal with large differences in perception have a large distance, and sound with basically the same perception have a small distance. Many perceptual distortion measures have been applied in the field of speech coding. Vector quantization is often used for quantization of speech coding parameters. After each frame of speech signal is analyzed by LPC, LPC coefficients, equivalent parameters such as reflection coefficients or LSP, are obtained to form a vector, and vector quantization is performed, which greatly reduces the coding rate. When vector quantization technology is applied in speech recognition, the VQ codebook obtained by clustering algorithm is generally used as a reference template for speech recognition. That is, each word in the system dictionary is used as a codebook as a reference template for the word. For any input speech feature vector sequence during recognition, calculate the total average distortion quantization error of the sequence for each codebook. The word corresponding to the codebook with the smallest total average distortion error is the recognition result. VQ-based speech recognition system has low complexity. That's all for this session. See you next session.